Hi there, my name is Kimberly Tong, and today I'm going to be breaking down the advanced suffix array computation algorithm from the textbook. As a side note, the beautiful weather in Davis is really causing my allergies to flare up. So if my voice sounds a bit funny, just bear with me. To compute the suffix array of text t, the algorithm in the textbook outlines that we're going to do this in several passes. In each pass, we're going to lexigraphically sort all the substrings of length L. And then every pass, we're going to double that length L. And so if we're doubling the length L every pass, then by the log nth pass, L is going to equal the full length of T. Or in other words, those sorted substrings will actually be the sorted suffixes of T. So I'm going to show how this algorithm works with some block diagrams and such, and I think it's best demonstrated by an example. So let's say that T equals the string rat-a-tat. The first step would be to consider substrings of length 2. So we'll have all those substrings listed out. We have RA, AT, TA, and so on. If you notice, each substring is composed of 2 characters. The first step of the algorithm is that we want to find a way to rank these substrings. And so the textbook uses a function called ord, which basically returns the ASCII values of the left and then the right characters in each substring. You can use any ranking that you want, but ASCII is very convenient for this first step. So that's what you see on the left-hand side here. We see for substring 1, RA, we're calling ord on the right substring and getting the ASCII value 114, and then we're calling ord on A and getting the ASCII value of 97, and then we're also going to hang on to that index. So because it's substring 1, we're going to store index 1 here. We'll also do the same with all the other substrings, where for AT, the ASCII value of A is 97, and with the ASCII value of T is 116. And then again, that index, that substring is 2. So once we have all our substrings listed out like this, we're going to sort them, where we're going to sort them based on these kind of ranking or ASCII values. And so this left character is going to have priority over the right character, but if needed, like you can see here in the sorted, well, actually down here, let's see, down here is a good example. Both these substrings have left's ranking value 116, but then we use the right value as a tiebreaker. Now that we have all our substrings sorted, we're going to make a rank array out of this. And we're already familiar with this from class. And so you can see that substrings 2, I'm just reading off these indexes here, substrings 2, substrings 4, and substrings 6, they're all tying kind of for first place. And so because of that, in the rank array, entries 2, 4, and 6, I'm going to put rank 1. It'll be similar all the way through the rest of the array. Now we're going to move into our next pass. Before we were looking at substrings of length 2, now we're going to look at substrings of length 4. So these are all the substrings listed out. And if we notice, each substring is actually composed of a character set that we've already seen. And we just calculated the ranks for all of those. So you see that RADA is decomposed into RA and TA, and we already got the rank for RA and TA, so we can just reuse those in our sorting. So yeah, just as I was saying, we're going to pull those rank values that we already calculated into our substring array. And so if we want to get the values for RATA, we're going to look at what's the rank that we calculated for RA that corresponds to a rank of 2. And so this left side of the substring has rank 2, and then the right side of the substring, TA, has rank 4, and that comes back from down here. Just as a side note, I have all this text here, but of course in the algorithm that's just all handled by indexes and stuff. But I just have the text for readability. Let's go through one more. If we want to calculate the values for ATAT, then AT, the left side, corresponds to a rank of 1, that we see here. And then conveniently, the right side is also AT, and so that'll also correspond to a rank of 1. And once again, we're storing that substring number 2. Once we have all our substring values, we're going to sort the array again, and that'll give us our sorted substrings. Once again, the left value has priority over the right value, but the right value is going to be used as a tiebreaker when needed. Again, we're going to make a rank array. The logic is very similar each pass. You see that in first place, we have substring 6, again, reading off this index. And second place, we have a tie between substrings 2 and 4. And I can tell that it's a tie because I see these values 1, 1, 1, 1, they're the same. So from this, we're going to construct our rank array. And finally, let's get into substrings of length 7. Normally, we're going to consider the substrings of length 2, then 4, and then 8, and so on. But because in this particular example, we're looking at a string of size 7, we're going to stop at size 7. So we have all those substrings listed out here. And again, you'll notice each substring is composed of a character set that we've already seen before. So rata-tat is composed of rata and tat, and we already have those ranks. So again, we're going to pull those rank values into our array so we can use them to sort. So for rata-tat, we want to look at the left side, RATA. The corresponding rank value for that is 3. So you see that here. And then the right side is TAT. The corresponding rank value is 5. And so we have a 5 here. And again, we're hanging on to that index. We'll do that for all of those 6 remaining substrings. So we have 7 substrings total because our size is 7. And then we're going to sort them. Yeah, just getting what we've gotten in each of the previous phases, except now we're looking at substrings of size 7. And you'll notice that actually these sorted substrings look exactly like the suffixes of T, our input string. And that's because they are. And so if you look, these are the sorted, too many S words. These are the sorted suffixes of T. And we know that once we have the suffixes of T sorted, we can just read off those index values, and that will give us a suffix array. So that's exactly what I'm doing here. I'm going to read off these index values, 6, 4, 2, 1, 7, 5, 3, and plot those into my suffix array and return that. And so that's the algorithm in a nutshell. Just to wrap things up, let's confirm the time complexity of this algorithm. As we said, we want it to be O of n log n, and there's log n passes, then we need each pass to be a linear time. And so the work we need to do each pass is to sort the substrings of length L. The textbook has this neat trick for doing this sort in a linear time using radix sort. The radix sort first runs counting sort on the right rank, and then counting sort on the left rank, and that's how it keeps it in linear time. So that was a really cool trick. Additionally, we need to obtain that rank array. That's going to take linear time. So for each pass, it's linear time. And then because we're doubling that length L every pass, that means we're going to have O log n passes, which means that our total algorithm is going to be O of n times log n. So yeah, that's the algorithm in a nutshell. Thank you for your attention.